exact same one logical thing sometimes. So I said,
All right, guys. So professor's out of town today, so I'm covering for the lecture, but she will come back on Wednesday for sure. So before I get started, we have recitation last semester. So from last semester, I got really familiar with everyone. For this semester, it's a little bit different. It's a math class. So before I get started, how many of you from ECE? Computer engineering? I would say EE and computer engineering. Sorry. Other major, maybe? No? Mechanic engineering? No? Okay. Yeah, okay. So today's lecture 50. So just run a few logistic. The course will be recorded today. I will put it on the YouTube so you can play. Yeah. So homework 7 is due this Wednesday. Our quiz on Wednesday as well. And sorry, homework 7 is due Thursday. Quiz 5 this week, and the readings on Courseweb as well. You should see that. All right, so quick review from last lecture. Any idea what is causal signal? Yeah. So it's actually causal signal. It's a signal Vt if there exists a value of t such that Vt is 0 for all t is less than t, right? Otherwise, it's non-causal. So how about these two? Is the first one causal or non-causal? Well, it's definitely non-causal, right? Because it's oscillating, right? How about this guy? Causal for sure, right? For t bigger than 0, it's 1. Then we have 10t, right? So for this guy, it's 0, t less than 0. All right, pick to pick. Any idea? Yeah, so that's the range between the maximum and the minimum. And the characteristic of this guy, this is always positive. How about VP? VP is just the max of the absolute value of Vmax and Vmin. All right? And how about RMS? You can use that a lot in your circuit class. Any guess? So if our power is described as 1 over R, so VM RMS is nothing more than P average in a period of t and do the integral over your power. Let's plug one of our outside the bracket, then you have this guy. Right? So that is your VRMS. Okay? So it's a measurement of the average power for the signal. Okay, so that's the quick review. I'm pretty sure you're going to use that in your homework 7. Let us know if you have any trouble with homework 1. All right, so the next one will be our topic. So we're going to cover 4 modules today, from bilateral to unilateral, and between that we'll have the last Laplace transform for the delta function, and the last part will be the rational functions. That's where leading us to find the pole and the zero of the system. Okay, so let's begin the first chapter. So that's the learning objective. You have it in your lecture. So what is the bilateral Laplace transform? So bilateral Laplace transform is really nothing more than we would write in this way: capital S, capital X, S, and we use the special alphabet represent the Laplace. Xt. This is really nothing more than minus infinity to infinity xt e minus st dt, right? And that means the Laplace transform, right? And you have to mention that for any complex number, for the whole range, that the integral will converge. Well, we'll talk about it in the next few pages. So the next one is the time domain, right? The small xt, you are all seeing that from past few lectures. That's just the signal that we describe in the time domain, right? However, in Laplace domain, it is the description for the frequency. Right? So we're basically shifting our perspective from the time domain to the frequency domain. So the next concept will be the region of convergence. So the Laplace transform will only exist for the converges that over a portion of the complex plane and the range of the value for the S that your Laplace transform will converge to a finite value, and we define that as the region of convergence. We'll also write that as ROC. And big question will be, why do we need Laplace, right? That's the first question you always ask. So let me explain this way. So the Laplace transform really tells us the relative amounts of complex exponential signal. This guy, e to the st, whereas it's a complex number, right? And we want to present within the signal xt by the equation that I just showed you here. Okay? So tell us how to make xt by infinite summation of the complex exponential signal. It's really the two-way perspective. One from time perspective, the other one is from the frequency domain. And after a while, Laplace is really good at looking the response to pulses, step function, which we'll talk about it later, and the delta function. Okay. And the second reason we want to do Laplace transform is usually in an engineering problem, the system is described by ordinary differential equations, right? And we all know that for our first midterm, we have description of system and we write it in the ODE. But the problem is, hey, this is really really ugly view. How do we solve this? We have to get back to tell whether this is homogeneous. Obviously, this is a non-homogeneous system. We have to get back to the formula sheet to get the basic rule, the modification rules, and to solve this by what we learn. But Laplace can really do a good job by transform the time domain problem into a frequency domain, right? And mathematic description of the system can be minimized or simplified, right? So from this equation, you can see that we can really simplify that the time domain to a Laplace domain, which is the frequency domain, by related by the polynomial equations we have in here, right? It's just a constant here. And actually, in the next few lectures, I believe for next week, you will do the transfer function for this. This is really nothing more than xys over xs. That's right. And for this one, we can see the system description more directly by finding the poles and zeros. And then we're going to do the inverse Laplace to get back to the time domain. And you can see the whole picture of the system. And the next one would be the frequency domain representation. So the Laplace transform can really simplify the problem of your output in response to your input. So for example, we use that a lot, the output voltage for an RLC circuit, right? And let me give you an example for calculating the bilateral Laplace transform. So let's see we have causal exponential functions, which you already know, right? So the Laplace transform, capital X, S. And we know the equation right now, right? Just learn. Minus infinity to infinity, xt e st dt, right? And we have xt here. Plug right in. We have e to the sorry. And you must be familiar with this guy, step function, right? Step function is really nothing more than t, right? Well, t is then we're going to revise this guy to 0. minus t. And there we go. And you would ask for doing this, right? That's nothing more than this guy. And let's further simplify that. The problem becomes right? And now the problem becomes, hey, how do we do this guy? How do we find the limit? Right? So let's do this way. Oh, by the way, S is a complex number. Right? Feel free to stop me if you have any question. Just jump right in. Okay. So the problem becomes this. And so if we look at the convergence, the ROC we just described. Yeah.
Can you just reiterate how you got rid of the negative infinity and put it to 0 with the step function for ut?
Because ut is only 1 after t bigger than 0. Okay. It's all 0. Yeah. See, this guy, right? Doesn't matter from this part. Yeah, so let's talk about ROC. So what do you think? Which part or which region that this function will converge to a certain finite value? So let's talk about it. Still running, still writing? Yeah.
So would it be for sigma plus a greater than
0. That will be the convergence area. Yeah, nice one. So we'll converge for sigma plus a bigger than 0. In other words, sigma bigger, right? So that's the ROC we have. Or in other words, will not converge for less than 0. So back to the equation. So our Laplace transform becomes this. This converge, like the gentleman mentioned here, converge to 0, right? So final Laplace transform becomes, and you should mention that your ROC is when sigma bigger than minus a, or we're writing this way, the real part of your S is bigger than minus a. And now we have the time domain description xt, right? And the other one is the frequency domain for the same object. And when I learned this the first time, usually take me a long time to grasp the idea of Laplace transform. And one of the professors just told me, hey, Honda, if this is a paper, I mean, if you look in this direction, what do you see? Just a line, right? But how about Laplace transform? Now you see a different view, right? From a line to a different page, right? And the same thing for you. I believe some of you take digital logic, or currently take digital logic. When we simplify the logic behavior from Carnot map, when you want to try to simplify from the sum of product, right? It doesn't really help you a lot with the main term you have. But switch to the other way, the product of sum, right? Doing the max term, then you get more simplified version of your Boolean expression, right? So that happens all the same to all engineering domain. So the Laplace transform, and in next we're going to talk about Fourier transform. It's just a way of methodology. We convert one thing to the other perspective. Okay, any questions? No? Okay, so let's do a quick example on unit step. How about talk to your neighbors for 3 minutes about this guy, how to do the Laplace transform of the unit step. So this is just a step function, and I put your equation for you. All right, 3 minutes.
It just changes the integral. This is a very
All right. Any volunteer? Any guess? Yeah. Great job. So it's 1 over s. So let's do this step by step. So the same thing, right? The step function we only care about when t is bigger than 0. So actually it's a little bit simpler than last example. Right? S is a complex number. Which is plus j omega, right? And the problem becomes right? So how to do this? First guess, if sigma is less than 0, our equation is this. Yeah, sure.
Thank you.
Yeah, it's okay. Okay. So, first guess, based on equation we have, Let me write here for you. Right? The sigma is less than 0. Should have t here, right? This is definitely infinite, right? Sorry. Sigma is 0. And this is 1. And remember our Euler equation, Euler identity, right? And the problem becomes cosine omega t minus j sine omega t. How about this guy? This is really oscillating, right? So does not converge. The only lucky candidate for this question is if sigma is bigger than 0. You will see that in the next few pages with the MATLAB. So you can see why that happens for sigma bigger than 0. That converge, all right? And that is 0, right? So, conclusion, our Laplace transform is nothing more than 1 over s, 0, minus 1. And I believe you got a correct answer, right? 1 over s. And don't forget to mention your ROC in your exam. For ROC, sigma bigger than 0, or you can write this way, your real part of your s is bigger than 0. Any question? Yeah?
How do you go from step 3 just to negative 1 over s is 0 minus 1?
Because this guy is 0.
Okay.
Right? Meaning this guy is 0. I expand S to a complex plane. So there you get S 0 minus 0. Yeah.
Will there always be an ROC such that that limit will go to 0?
For the ROC, sigma is bigger than 0. You have to specify that, because when sigma is less than 0, it's not going to converge, right? It becomes infinite. Yeah?
Why does the imaginary part converge to 0 when sigma is greater than 0?
That's a good question. Yeah, maybe you can see the MATLAB plot. Maybe easier for you to see. Okay. Any more question? Nope. Okay. So next part will be the MATLAB. First guy is just plot the step function. The other one is the amplitude and phase. All right. It should be straightforward. So this is the code. Let me zoom a little bit for you. Right? You can follow the same style in homework. It should be that hard. All right. So that is your VT time domain, it's a step function. So next one will be your magnitude of after your Laplace transform. So you can see here that the Laplace transform for unit step is just 1 over s, right? And for the real part of your s, only makes sense when your real part is bigger than 0, and for imaginary part, it really doesn't matter at all. Right? So that is the imaginary part of your s. That is your real part of s. And here we go with the face. And the next function we want to see is the impulse function. So you all know the impulse function. We call it delta function. And there are three useful properties for the Laplace transform for Dirac delta function. The first one is called sampling theory. Should be clear. The first one, make sure your xt is a continuous signal, or the other one is xt times your impulse function, and that is nothing more than because t is 0 for t is not 0, right? So that is the key part. So we're going to apply this sampling property to a Laplace transform. So the shifting property. So if we do the transform, sure. It's a bit too fast than professor style. All right. So we do the transform of the Dirac function. And you put xt out. And the useful function you can remember, this is like theorem here. This guy is 1. So that will give us x to the t0. I believe that we will provide that in your formula sheet for the exam. That's the useful theorem you have. The third one will be the Laplace transform. Coming back a little bit. Oh yeah, sorry. All right. So let's do Laplace transform. So we have xt is the impulse function, and the Laplace transform of capital X is nothing more than classic equation for Laplace. T0, right? And you move this guy out. And there you go. We just have this always 1 from the shifting theorem, right? So your Laplace will have this guy. If t0 is 0, we have our Laplace is 1, and your rock will be all complex plane. So as far as now, we'll all see the Laplace transform is like bilateral, right? From minus infinity to the positive infinity. So next chapter, we're going to talk about the unilateral Laplace. Because usually in the engineering problem, the domain will focus on t bigger than 0, right? We don't have application based on minus infinity to positive infinity, right? So here's the definition that for unilateral transform. The same xt, well, your Laplace transform is nothing more than to the lower bound xt e to the minus st dt, right? And the lower limits is nothing more than this 0 minus sigma here. So basically, we're including the impulse at t is 0 in this integral. So how do you compare these two different Laplace transforms, the unilateral and the bilateral? That's the question you might ask, right? Well, bilateral described as the small letter b here, and this guy represents the unilateral. Let's jump to the right next page. So if xt is 0 for t less than 0, so how do we compare? It's actually pretty simple. Our bilateral becomes, Laplace transform becomes xt times your step function, and it's really 0 to infinity here, dt, right? Our unilateral becomes xt, and that's exactly 0 to infinity we just described earlier. And that gives us, for the unilateral, xt equals to your bilateral Laplace transform multiply your step function. It should be straightforward to understand, right? Basically cut the plane in half by the step function. And the other one will be the application, next page, okay? In other words, why we need unilateral Laplace transform, right? Because in RLC circuits, we usually care about condition that t is bigger than 0, right? Or suppose we're given the initial condition for the circuits that yt at some initial time, such as y0 is c0, and the first derivative will be nothing more than c1, blah, 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 right? So in other words, we have the initial time as t is 0, right? So the unilateral Laplace transform can represent each of the signal in the frequency domain. That's true. And the simplified analysis, because we may able to ignore the region of convergence, assume that all exponential terms converge to 0, right? So that's just the one side of the Laplace transform. We don't care what's happening previously before 0. So that's the usage of unilateral. Okay, so we have the example of 3 step function and one-side exponential and the impulse, right? We all sorted out, the ROC of them, and you probably need to put in your cheat sheet in your exam, or should be easy to remember actually. So the next example will be the cosine of bilateral transformation. So let me write this for you, and how about try 5 minutes, and we'll see. Cosine equal t to the Laplace transform. Okay, find the ROC as well, region of convergence. Okay, 5 minutes. I would suggest you guys to do the Euler identity for this cosine omega t. Yeah, let me do one step for you. This is all right. That might be easier for you to solve. Feel free to talk to your neighbors.
I know there's like different similarities there. I don't know the differences that you're it's not always the same. In this case, don't use this. How this
you probably figure out there's a significantly difference between the bilateral and the unilateral for this particular question. Bilateral is really not going to work, right? All right, how about sit down and do it step by step? Okay, so there you go with, let's expand this guy. It's minus j omega t. T. All right. And all you have is 2 to the s to j omega. Now we're doing the unilateral Laplace. Right? But it's just two parts. Next page. Okay, so now let's talk about it. If your real part of your complex number is bigger than 0, converge, right? If your is less or equal than 0, not converge, right? So what is the final solution for the unilateral? So it's nothing more than basically converge to 1. Same thing here. And that gives you, now you are expert in the complex calculation right now, right? Square, please. And that will give us the final results for the one side, unilateral. So how about bilateral? Want to guess why that doesn't work at all? Bilateral. So here you go. So if we do the integral for this guy over here from the two extreme, right? Minus same thing, two extremes. So this is the case 1. If your real part is bigger than 0, that gives us infinite, right? Same thing here as well. If we go to the other direction, to the positive infinity, what's the results? It's actually infinity as well, right? There you see the problem with the bilateral Laplace transform, right? It's not going to work. Does not converge at all for bilateral Laplace transform. So that's the problem. Now you see the difference between two different methods, right? So there you go. That's the MATLAB for the cosine. This is the code, and you see this is the time domain. It doesn't really matter for t is less than 0, right? Go after 0, it's just normal cosine. So that is the Laplace transform. Yeah.
For the difference between the unilateral and bilateral,
Mm-hmm.
is the reason the bilateral doesn't converge because the cosine is an oscillating function?
For this particular question, yes.
Will that be true of all the trig functions?
You have to see. Yeah, it's application specific. Okay. Right? So that's your amplitude. Remember our results? Our result is the final Laplace is second order. We have two poles in here. We'll talk about the poles a little bit later. That's why I have two peak here, and this is the 0. And this is the 0. This is the pole. All right. We have two imaginary poles. Right? Don't worry about it. We'll talk about poles right after. So this is the face. Did Professor post the code for last lecture, or nothing at all for code? What do you have?
Post what?
Code for MATLAB code.
For what?
For either homework or lecture.
I don't know if she did.
Okay, let me ask her. Maybe we can post a code for this. Okay, right. So there you go with the rational function. So many Laplace transforms, the final results can converge to your polynomial type like this, like the Laplace for the step function, for the exponential, for the delta, a direct function, and for the one-side cosine function. You all have this kind of rational function. Oh, by the way, I don't think we plot for the exponential. So this is the exponential for MATLAB, right? This is time domain, and this is the amplitude. Oh, this is the phase, sorry. And that is the amplitude. And if you see carefully, what is your final result? This is the final result for the exponential, right? So if you look at the amplitude, that is actually due to the minus a, right? Well, for this problem, the plot is come from a's 1, right? So it's not really like the step function, whatever bigger than 0 makes sense. So we have a shift in the frequency domain as well. So that's the plot for all 4 functions. That's like the 4 ground truths, like deep cornerstone of Laplace transform. Okay, so the very last section for today's lecture will be the rational function. So what is rational function? Rational function is a function can be described in the ratio of polynomial, which your numerator and denominator here. Zero. Right? So all the functions we have, that's the basic form of the rational functions. And the the rational function is going to tell the basic characteristic of the system, whether how many poles we have, how many zeros we have, and based on the number, we can tell whether the system is stable or not. Okay, well, that's for next lecture, the characteristic of the rational function. So, the factor numerators and denominator. So basically, describe that in terms of roots. Your constant. ZM stands for 0, and P stands for how many poles do you have. Oh, sorry, I think I need to mention the right. So the root of ZM of numerator are the poles of XS. So in your exam, probably professor going to ask you how many zero, how many poles in this polynomial, right? So what you have to do is just describe your polynomials in the form of their roots. So that is the effect of zero and poles. So what pole can do is they look like a tent post holding the surface. Unfortunately, I don't have a MATLAB graph for describing this like tent pole. I'll maybe try next time, next lecture. For the zero, it's like 10 sticks, right? You have to visualize what that looks like. For any other value of your S, the surface of your Laplace transform will just change smoothly. So let's do a quick example of this guy. So you have your transfer function, right? Oh, I think I just talked about it. Transfer function is the ratio of the output to the input of the system. So ys is your output, xs, that will be your system input, all in Laplace transform type. And the ratio will be the transfer function. So you have the polynomial for your numerators and denominator. Think for a minute, how many poles or zeros for this particular system? The first step will be just go to the type that to the roots format, right? How many roots it contain? Your numerator, right? That would be straightforward, right? So your S is nothing more than, right? So, or write it this way, plus or minus J. So what are the zeros? We have two zeros, right? The first zero will be the positive J, and the other one will be the minus J, right? On two directions of your complex plane, right? So write specifically, zeros are, first zero will be J, second zero will be minus J. All right, that should be simple enough. For, oh, should I wait? Wait for a few seconds. Then we'll go to the denominator of the system, right? Denominator is nothing more than factor 1s out of the bracket. How many poles we have? First time, students always make mistake for this guy. Let me write this more nicely. Sorry about that. Evan? Well, Evan is not responding. Okay, Evan, you want to try? Evan. It's okay. Ryan, you want to try? Well, what's the one? What's your question? Answer for this. Which one? For the pole.
Just one pole.
Really?
Yeah, -1.
Really? Okay. Well, that's a nice approach. Other suggestions? Yeah.
2 poles since one is a double root.
Well, not really a perfect answer. Any guess? You want to try? Yeah.
-1 and 0. -1's a double root, and s equaling 0 would make me.
Oh, that's a marvelous solution. So we have 3 poles in here. Let me change the color. Okay. S is 0. Don't ever forget this guy, right? This tiny s here. S is 0. And for this one, so s is -1. It's repeated. Right? So what are the poles? Pole 1 is 0. Pole 2 and pole 3 is -1. Even it's repeated, you should write that in your solution, right? So, very final plot today will be your complex plane. How to describe your poles and 0 in the complex plane. We know we have a 0, we have 3 poles, right? We have two zeros, which are either plus j or minus j, right? 1, -1, so that's imaginary coordinates. And for the real part, that's nothing more than 0 here, right? And the gentleman just suggests we have a repeated -1, right? So that's pole, right? We're going to do it twice, so make sure. So from the plot, you see all the poles and zeros are nicely described here. So in next lecture, we're going to talk about how to use the poles and zeros to describe the system, whether it's stable or not, whether it's get any functions we want, and yeah, that will be on Wednesday's class. And don't forget, we have quiz on Wednesday. Okay, homework's due on Thursday. All right. Today's lecture will be posted on YouTube or with annotated version, so don't worry about it. See you guys on Wednesday.